Hello, we will now do chapter 5 review worksheet. And so I encourage you to try to do these problems, pause the video, try to do them, and then check your answer as I work through them. So chapter 5 deals with basic probability. Today we're going to be looking at three of the main sort of problems that we have to do in probability. We got your Venn diagram problem, you got your tree diagram problems, and you got your two-way table problems. So yeah, you sure do. So anyway, so here we go. So this one says 56% of people in a village speak Russian, 36% of people in the village speak German, 31% of the people in the village speak both Russian and German. So it's giving you the probability of the one thing, probability of the other, probability of both. And whenever that happens, there's a really good chance the Venn diagram is the way to go. If you randomly select someone from the village, which probably they speak Russian or German. And so we'll make a Venn diagram out of this, and it will allow us to answer a number of questions actually, and it's considered showing your work for doing that. So make a Venn diagram. So we'll make one circle representing Russian, another circle representing German. So I'll say R for Russian, G for German. And so we got 56% speak Russian. So I'll put 0.56 at the top of that Venn diagram, and then 0.36 for the German. I'll put that at the top of that circle for German, and then 31% for both. That's this football shaped region, the overlap 0.31. And so then to fill out the rest of the Venn diagram, I can subtract 0.36 minus 0.31. That's 0.05. That's this crescent shaped region here that's in the German circle, but not in the Russian circle. Notice the two parts add up to the whole. And then say 0.56 minus 0.31, that'd be 0.25. That represents people that speak Russian, but not German. It's in the Russian circle, but not in the German circle. And then lastly, what about the outside? Well, the whole diagram has to add up to 1. And so when you add this, this, and this, and the outside has to be 1. So if you say 1 minus that, okay, that's going to give you 0.39. Okay, the insides add up to this plus this add up to 0.61. And so this is 0.39. So there's your whole Venn diagram. So the first thing it asks, if you randomly select someone from the village, which probably they speak either Russian or German. In other words, that's the area inside these two circles. And that is just going to be that plus that plus that, which is 0.61. But using the addition rule, which is on your formula sheet, which you also need to be able to do, the probability of Russian or German, that means or means add. So that's be the probability of Russian plus the probability of German minus the overlap, probability of Russian and German. Because by adding these together, you counted the overlap twice. And so you have to subtract it off once. So the probability of Russian is 0.56, the probability of German is 0.36, and then minus 0.31, and that is equal to 0.61. So 61% can speak one or the other or both. And so that is how you do that. Number 2. So number 2 says, what percent of the people speak Russian but not German? Russian but not German is 0.25. Okay, that's all there is to that. Having the Venn diagram showing your work, or to show your work, you could say Russian 0.56, but not German. So you got to subtract off Russians, the people who speak Russian, also can speak German, minus 0.31, and you get 0.25. But that's the answer, number 3. All right, so number 3. In number 1, what percent of the people speak neither Russian nor German? And that's this 0.39. It is 1 minus the probability that speak either. And that's 0.39. The probability of neither is 1 minus probability of either. Okay, so that is that 0.39. So that's all there's to number 3. Number 4, in number 1, what is the probability that a randomly selected person in the village will speak German given they speak Russian? Number 4, the probability they speak German given Russian, and that's on your formula sheet. All right, and what that would be is the probability of German and Russian over the probability of the given. So these given ones are always going to be the probability of this and that over the probability of the second one. Well, German and Russian, that's 0.31. And the probability of Russian is 0.56. And so that, in fact, is equal to, I do believe, 0.5536. And thus, that's the answer to number 4, which leads us to number 5. There are 4,000 people in the village in number 1. What is the probability that 3 randomly selected people will speak Russian? All right. Well, What's the probability that one of them will speak Russian? Well, that's 0.56, but we need the number that can speak Russian. There's 56% that can speak Russian, and there's 4,000 people. So the total number of the 4,000 that can speak Russian is going to be 2,240, okay? So the probability that the first person selected speaks Russian is gonna be 2,240 over 4,000, which is 56%. Now, given the first one speaks Russian, the probably the second one's going to speak Russian is 2,239 because we took one of them out over 3,999. You have to subtract one off because we just took one of them out. Now, given the first two speak Russian, what's probably the third one speak Russian? Well, there's only 2,238 left that speak Russian because I took two of them out, and there's only 3,998 total people left that speak Russian. And so we multiply. When you have a multiple event, you multiply. So we multiply those three things, and those three things, when you multiply them, is 17551. So about a 17.5% chance that that would happen. Thus, that completes number 5. Number 6, show whether or not they're independent. Okay, well, there's a couple of different formulas. So you could show this, that the probability of, if they're independent, okay, if they're independent. Independence means the occurrence of one is in no way associated with a change in the probability of the other one occurring. So if they're, and you just have to memorize this. If they're independent, the probability of German times the probability of Russian is equal to the probability of German and Russian. The probability of one times the probability of the other is equal to the probability of both. And so this would be 0.36, and the probability they speak Russian is 0.56. Those are given in the problem, and the probability of both is 0.31. Now, are those equal? Well, when you multiply those two things, you get 0.2016. That's 0.2016. That is not equal to 0.31, and so therefore they are not independent. The other thing you could do, if they're independent, the probability, if they're independent, the probability of one given the other, let's say German given Russian, is just going to be the probability of the first one. Okay, the probability they speak German is 0.36. The probability they speak German given Russian is 0.5536. So if I told you someone speaks Russian, the probability they speak German goes up from 36% to like 55%. So therefore, they're not independent because those are not equal. Okay, so that's the other way of showing independence. And so there we go. And that completes our little Venn diagram problem. So, okay, so let's look at number 7. So number 7 says 60% of students at a college live on campus. If they live on campus, the probability they eat at the school dining hall is 0.8. If they don't live on campus, the probability they'll eat at the school dining hall is 0.1. If you randomly select a student at this college, what's the probability they eat at the dining hall? Okay, this is a tree diagram problem. Tree diagram problems are when you're given conditional statements, when you're given the probability of one thing given another. And that's what this statement is. This is the equivalent of saying, given they live on campus, the probability they eat at the school dining hall is 0.8. And when they give you conditional statements like that, let's make a tree diagram. And so this is how we would make a tree diagram. So we would say, first of all, okay, the first event we have is whether or not they live on campus. And so I'll put C for campus. There's a 60% chance that'll happen. So that means C complement, and the probability they don't live on campus is 40%, okay? So given they live on campus, the probability they eat at the dining hall, I'll put D for dining hall, is 0.8. And so that means given they live on campus, the probability they don't live in the dining hall is 0.2. So given they don't live on campus, campus complement, the probability they eat at the dining hall is 0.1. Therefore, given they don't live on the campus, the probability they don't eat in the dining hall is 0.9. So now we can find all the probability of all 4 of these events. Okay, so the probability that someone lives on campus and eats at the dining hall, and in math means multiply. So this and that is you just multiply the 2 limbs to get there. So that'd be 0.6 times 0.8, and so that's 0.48. Okay. The probability that a randomly selected person will live on campus and not eat at the dining hall. Okay, that's going to be 0.6 times 0.2, and that's 0.12. Notice these 2 things add up to 0.6. All right, what's the probability a randomly selected person will not live on campus and eat at the dining hall? Well, that's going to be 0.4 times 0.1, and so that's 0.04. That's 0.04. Yes, 0.04. And so then what's the probability that someone does not live on campus and they do not eat at the dining hall? That is 0.4 times 0.9. And so that's 0.36. And so there we go. And those add up to 1. So the question is, what's the probability they eat at the dining hall? Well, this event and this event they eat at dining hall right there. And here's the other event they eat at the dining hall. So with and without living on campus, right? And so the answer to this would be, so the probability they ate at the dining hall is going to be 0.48 plus 0.04, and that's 0.52. And so that's the answer to number 7. Answer to 7. Okay, so there we go. So let's go to, so then it says number 8 and number 7, if you randomly select a student at the college, what's the probability that they will live on campus given they eat at the dining hall? Okay, given they eat at the dining hall. So number 8, what's the probability that they live on campus? So it's a reversal of a conditional. This is in essence a Bayes theorem problem, which we can just use a tree diagram for this. Well, our little formula for the conditional is the probability of both of those things, C and D, over the probability of the second one of the given. Well, C and D, that's what that is right there. That's 0.48. Okay, and then this probability of dining hall, we just found there is 0.52. And so that, in fact, is equal to 0.923077. So if someone's eating at the dining hall, okay, there's about a 92% chance they live on campus. Okay, so so these are distinctly not independent events. Number 9. So number 9 says, if you randomly select a student at this college, what's the probability that they do not live on campus given they do not eat at the dining hall? So what's the probability they do not live on campus given they do not eat at the dining hall? That'd be that. Well, same formula. That's the probability of both of those things, not living on campus and not living in the dining hall, over the probability of not living in the dining hall. Well, those two things, this thing, this and that, well, that's just this. That's 0.36. So that's going to be 0.36. And then over the probability of dining hall, well, dining hall occurs here. No, I'm over the probability of not dining hall. Well, that occurs here, 0.12, and there, 0.36. So the probability of dining hall complement or not dining hall is going to be 0.12 plus 0.36. And so that is equal to 0.48. So this is 0.36 over 0.48. And that is equal to 0.75. And that is the answer to number 9, which leads us to number 10. Okay. In number 7, what is the probability that 4 randomly selected students will not live on campus? Well, the probability that they live on campus is 60%. So the probability they don't live on campus is 40%. Well, what's the probability that that's going to happen 4 times? Well, that is just going to be 0.4 to the 4th power. Okay, whereas we don't know the total number of people. Like back up here in regards to number 5, we knew there was 4,000 people. So we did this thing to where we subtracted, we subtracted 1 each time from the total number. Here we don't know the number. Okay, so we just know there's 4 of them, so it's just going to be 0.4 to the 4th power, and so that is equal to 0.0256. So that is that. Number 11. We're sort of assuming an infinite population there in a way. All right, and then number 11. Okay, this is 2A table problems, and so these, I think, hopefully are pretty intuitive for you. Hopefully you can just sort of reason these out. And so whenever you encounter a 2A table problem like this, I think it's a good idea to come up with a marginal distribution. So what we've got here, the vehicles made at 2 factories are all either cars, pickup trucks, or SUVs. One of the factories is in Texas, the other is in New York. Here are the numbers made at the factories in the past year. So in Texas, there's 56 cars and 86 trucks and 64 SUVs and so forth. So whenever you're doing a 2A table problem, we need to come up with the marginal distributions. We need to add up the rows and columns. And so let me do that right quick. And so we've got Texas, and we've got New York, and we've got cars, we've got trucks and we've got SUVs. And so this is 56 and 46. And so those, there's a total of 102 cars. And then trucks, we've got 86 and 12. So there's a total of 98 cars. And then SUVs, there's 64 and there's 28. And so that would be 92 SUVs. And you add all these up, there's a total at the two factories of 292 vehicles. Then you add up the rows. You add up the rows, 56 plus 86 plus 64, that's 206. And then 46 plus 12 plus 28. And so that's 86. There's a total of 86 from New York. And now I should be able to answer any of the questions. So the first thing is, if you randomly select a vehicle from this table, what's the probability there'll be a car? Well, there's a total of 102 cars. So the probability of car is just going to be 102 out of 292. And that's considered showing your work. You can leave it, you can leave it just like that if you want. That's equal to approximately, 0.34932. Number 13. So number 13, it says, what's the probability to be a truck from Texas? A truck from Texas. Well, a truck from Texas, that's those 86. There's 86 that are trucks from Texas. So the probability, that it'll be a truck and from Texas, that's 86 out of 292. And so that is approximately equal to 0.29452. Number 14, we are getting there. So it says a truck given that it's from Texas. A truck given that it's from Texas. So we can only look at these Texas vehicles. And what's the probability that's a truck? So we can only look at these 206 vehicles that are from Texas. If you randomly select one of these 206, what's the probability that it's going to be a truck? And so the notation there, 14, and so they both start with T. So it's the probability that it's a truck given that it's from Texas. So we can only look at the Texas vehicles. If you randomly select one of these 206, what's probably the truck? So it'd be 86 out of 206. And so that is approximately equal to 0.41748. Okay, 41748. Number 15. So what is the probability that 3 randomly selected vehicles will all be from Texas? The 3 randomly selected vehicles will all be from Texas. Well, from Texas, there's a total of 206 vehicles. So the probability that the first one will be from Texas is going to be 206 out of 292. Now, given the first one's from Texas, the probability the second one's going to be from Texas is now 205 out of 291 because we took one of them out. And then given the first 2 are from Texas, the probability the third one's from Texas, there's only 204 of them left. And there's only 290 total of them left. So you multiply those 3 things. When it's probability of a multiple event, you multiply. And so when you multiply those 3 things, you get 0.349605. So about a 35% chance that will happen. And lastly, number 16, show whether or not being from New York and being a truck are independent on this table. Okay, so one way of showing independence would be to say, well, you could say if they're independent, the probability of one given the other, let's say New York given truck, is just going to equal to the probability of the first thing. That's one way to show it. And so the probability of New York given truck, well, given truck, the probability is from New York would be 12 out of 98. So this would be 12 out of 98. But what's the probability that if you randomly select one of these vehicles, that it'll be from New York? Well, it'd be 86 out of 292. So 86 out of 292. Are those 2 things equal? Well, as it turns out, this is equal to about 0.1304, and this is equal to 0.2945. Those are not equal. Therefore, they are not independent. The occurrence of one changes the probability of the other one occurring. And that's it. That's your quick little run through from chapter 5. Thanks for watching the video. If you got any questions, please send them to me. I hope you have a great day.